build something bigger, but we have problems with scalability because we require consensus, and in particular, they're way too slow and expensive for any kind of ML models with other kind of roll-up logic. And then ZK lets us take trustlessness, decentralization, and composability. It's a different kind of composability in some ways, but it's in many ways as powerful. So you can imagine some future where lots of composed ZK stuff happens, kind of like a roll-up, but maybe in a more chaotic kind of tree kind of way, DAG kind of way, and then it gets occasionally checkpointed back to the chain. But it has this wonderful scalability property that once I prove something, everyone can believe it. It's incredibly energy efficient, even though each individual proof is annoying and expensive and uses a lot of compute. But at the moment, this is all very bleeding edge stuff. We have lots of weird languages. The circuit model is an unfamiliar programming model for most people, until concluded, and a lot of difficult math and security. And for those who were in the beginning, we saw one of those difficult math, right? Yeah. So what are we doing with ZKL? We're trying to make it possible to run AI and ML models effectively on chain pretty easily. We all know about ECDSA signatures. We take the public input, we take the private key, we run the signature function, and we get a public result and a signature, and then the chain verifies it. And with general purpose ZKP or in particular ML, what we're doing is replacing the signature function with the machine learning model. We could do any function or any computational graph, but we're sort of focused right now on machine learning models. And we're trying to make it so that you, as the user, you can work in Python to define the computation you want to do, somehow describe the pipeline, or that's stuff that we're actively building, and then compile it with this tool and deploy it. So we generate the verifier, generate everything really easy. And then we can get all the positive things of those three of AI on smart contracts and so yeah, the loop, we think of it as like a loop. There's like an ingestion thing where we pull some data in. I think a lot of the hackathon stuff that we're looking at this week, it can be signed or a tested ingestion, but it could also just be anything. It can be just a picture you take or a piece of text or whatever. There's still interesting use cases. You prove the inference, you verify it on chain, and then you do something. You let a smart contract fire off, you award a prize, you fire some kind of index hook. And my sort of inspirational, why do we care about ZKML, is that I think it's a way for us to let the blockchain perceive the physical world, to give it sort of eyes and ears, let it eventually solve this identity problem, make it so that we own our assets kind of because of who we are, not because of something that we know, in a way that can't be severed from us. And I think that's really exciting, but it'll take 10 years to build it, so we have to do a lot of intermediate stuff. And then the big picture is kind of, well, let's put the smart back in smart contracts and let them actually exercise some kind of judgment as to whether our condition was satisfied in a soft way, not just a black and white binary way. And as we talked about already a little bit, it's interesting for parameters and input to be either secret or public, depending on your model. If you're doing a candle, if you're doing an identity model, if you're doing like an on-chain vault or something like that. I'm going to not talk about the application examples yet, but maybe I'll come back to that. Let's talk about, I thought we could just sort of go through a little bit, and I'll talk about parts of it. And please interrupt me with questions. This is actually a nice small group, so.
I actually had a quick question.
Yeah.
Just about the uncertainty of results in an AI model. Are there any ideas about, I want to say, making up for erroneous decisions by AI, especially with something that's irreversible on a smart contract?
Yeah, that's a good question. I mean, I think one of the we mostly think about like the exciting parts about crypto and blockchain, right? We don't just like in the early days of the internet, we were really excited about the idea of citizen journalism. Anybody can write, what they think is true, and then we're like, oh shit, now none of it's true anymore. Like, just writes whatever, right? There's always downsides to technologies. I think one of the downsides to making the chain smarter and putting more intelligence to the chain is like, who do we appeal to when something goes wrong? Right? I think we should think when we're designing these systems about how do we deal with a situation where the chain makes a mistake? You know, is there a Supreme, if we're making smart contracts judges, who's the Supreme Court? You know, what kind of thing can we do? So scalability, great, but it should also have some kind of a leash on it. Otherwise, we're creating trustless, unstoppable, you know, on AI on chain that you can't unplug, and that could go badly.
Out of timeline.
Hopefully not. But. Okay, so this is ZKL. We have 8 contributors, 9 contributors actually. One's not there, and I have some people today who become contributors. It's an open source project, Apache. We have lots of tests that are passing. I think tests are really important. So one of our biggest expenses, or significant expenses actually, is tons of GitHub runners and other things to run lots of tests, because this stuff is very computation intensive, but we want to make sure we check everything. Okay, so what is it? It's a command library and a command line tool, probably seen in a Python library for doing inference, proving inference in deep learning models, and other computational graphs inside of a Snark. The workflow is we define our graph, usually using Python, neural network and PyTorch or something else. We export that as an Onyx file and some sample inputs. And I said before some people came that we need an Onyx file doesn't always fill in all the dimensions, so we need a sample input in order to be able to infer what all the dimensions in the network would be of the tensors. And then we point Ezekiel to the Onyx file and the JSON file to create a circuit, and that's kind of an abstract thing. Actually, every time we run it, we're creating a circuit, and so we need to create a circuit and a verifying key. In some sense, the circuit is defined by an Onyx file itself. That's our intermediate. That's our circuit description language. And one of the reasons I'm excited about this particular, or made the choice of this particular angle, is that if you are used to working with tools like PyTorch and TensorFlow, you're already in a sense comfortable with circuits, because every neural network is just a circuit. It's a computational graph. It's a directed acyclic graph. It doesn't usually have loops or conditionals at inference time or training time, and so I think that that impedance mismatch, the gap between people who are used to writing regular code and people who are used to writing Snarks, is actually smallest people with a machine learning background, because you already think about everything in terms of circuits. So that's kind of the thing that we're exploiting to try to make the friction smaller. Then you can generate a circuit, and you can do things like say, all right, I ran this publicly available neural network on private data, and it produced an output. Maybe that unlocked a key, I won a prize or something. I ran a private neural network, like in your example, where I want to prove that I have a good enough network to solve some problem on public data, and it produced this output. Another scenario where even that might work is something like we're trying to, outside of blockchain, we're trying to prove that our AI is not biased. Like, I'm in TSA, I'm never going to tell you what my algorithm is for selecting people for additional screening, but maybe I can be convinced to prove that my model doesn't discriminate based on race. Or it could be all public. And the case for all public is kind of the roll-up case. Right? So where we want to do some computation that's too expensive in Solidity, we don't care if everybody knows what the input and output of the computation is, but it's just purely we're trying to save gas. And if you really want to, you can dig into the library and you can actually use it as kind of an API for writing circuits directly instead of using the Onyx front end. Or you can make a new front end for some other description language. Okay. Please contribute, ask questions, open issues, open PRs. If anybody wants to do it, I will help you do that. And some other folks here that have contributed can help you too. Sorry, we use nightly. And so then do bus step override set nightly, do maybe like a cargo install -- path dot, or you can build and then move your binary around. There's docs. The docs look like this. Every function is documented. Every struct is documented. Anyway, so please use that if you're trying to get oriented. And then we have a command line interface to load the Onyx files. and we're using Halo 2 as our backend. I hope that, so one of the more ambitious goals over the next few months is to how to expand our backend a little bit and maybe use some of these other systems like Lumpy 2 or Nova, Supernova, or something else as an additional, or Circom as an additional backend. And because we're sitting in the middle like this, the Onyx files won't change, but you can just choose a different compile target. I'm trying to think of it like a compiler for Rust or C++, whatever, where I can say, I run this on my Raspberry Pi, or I want to run on ARM, or whatever. We think about proof systems like hardware. Yeah, okay. And there's Onyx files. There's a really bad PyEZKL repository that will get good soon. We're still working on bindings for Python. Right now, all it does is help you export things. Maybe actually I'll okay. Sample files are in example Onyx. Actually, I will show you one of these files. So, okay, here's like some really simple one. So you can think about there's a Python function that will generate. We get an input, which is just describes the shape of the tensor, some input data and some output data. And that's used in creation of the proof. We can use a network.onyx file. This is binary file, but you can see there's not that much going on in there. Right? And sometimes you can sort of see what's happening. But you can see why there's no shapes or anything. That's why I have to do the forward pass to figure anything out. And this one, the Python that creates this is we import Torch and we import this export. We define a neural network model just like we always would. Like this has a convolutional layer. Question?
So can you use any Onyx, or do you have to generate it with the
No, you can use, in theory, you can use any Onyx.
Okay.
In practice, we have not implemented, Onyx has 1,000 or 2,000 different ops. We have not implemented all 2,000 ops.
Okay.
We implement more with great frequency, 4 or 5, I think we implemented in the last 24 hours, but
Okay.
some will work, some will not. If there's one that you find that you'd really like to work, feel free to send it to me and we'll try to get it working. Because usually, so this is actually really, and this is actually kind of a deep question. So what's the work required to get it working? Some of it is plumbing. You read the Onyx file, you see a string that describes a node, and you figure out what you need to do to implement it, right? So the way Onyx works, even a very simple graph like this, right? This is a convolution. So what's the data of a convolution? There's a kernel, convolution kernel, and there's a bias term. And so what this simple one-layer network will expand into several nodes. There'll be an input node. There'll be 2 constant nodes, one for the kernel and one for the bias. Then there'll be a convolution node that just says, hey, can all these things use these 3 inputs? Use this input, use this kernel, and use this bias. Combine them just like a gem or something. Combine them according like a generalized matrix multiply. Combine them according to this rule, and then produce an output. And then above that, there'll be an output node. So that one node will unpack into a bunch of things. So when you're figuring out how to implement a node, you look at the convolution node and say, okay, I got to figure out which inputs go where and what they do. Some of the inputs might be floating points. Some of them might be shape parameters, like integers and stuff. Okay, so that's part of it. That's just like the plumbing part. And then there's a math problem, which is some things are very easy to implement in terms of turning them into systems of polynomial equations, and some things are very tricky.
Yeah.
Like we're always surprised when you first get into ZK that a range check is pretty difficult, right? Like so something that was trivial, like which is the max of these, or is this thing greater than this, suddenly becomes a headache.
Okay.
Right? And so we're in a completely different computational model, and so some things we have implementations of, some things we know how to implement but haven't done. Some are going to take a little bit of research to get them right.
Okay, makes sense.
Okay, let's go back to README. So we can generate our structured reference string, or we can use an existing one. I'm going to skip generating this structured reference string because let's see. Oh, it's actually broken. All right. So yeah, you can have powers of tau. So in this case, I'm using, for example, a perpetual powers of tau 17. Actually, you know what, I'm not going to. I'll follow the readme and I'll skip ahead. That would make more sense. Okay. All right. So I'm just going to skip generating because okay. So I should say what's going on here. For testing, it's perfectly fine to generate a structured reference string. If I generate the structured reference string and you produce a proof, I can believe your proofs because I didn't tell you what my tau was. But if I generated the structured reference string, I know the tau, I can produce false proofs. Okay. So a general ceremony is like 1,000 people participate. If any one of them is honest, we can all trust the result. If you personally contribute to the ceremony and you know you threw your contribution away, you know you can trust it. So
you said that if all of them not cheating.
if at least one is not
At least one,
cheating,
yes.
yeah, you just need it's only any trust assumption. But you can also think about that as another tool you can use to create asymmetry in your crypto system, right? So if you want to create a proof, which some people can kind of produce a proof of anything you like, and other people, like you can control who the verifiers are in a sense by choosing that.
Okay.
But it's fine to use for testing. In production, you want to use a public ceremony. Or money is on the line. Not that you should use this if money is on the line, because it's alpha software. And okay, so then this is an actual proof command. And I'm gonna, before I run it, I'm gonna like walk through what the parts of it are so far. Okay, ZKL is a binary, bits equals 16. What does that mean? Okay, so this is like one of those rabbit holes that I'll decide how far to go down. Okay, but when you have a neural network, the first approximation, what is a neural network? It's you have a matrix of parameters, you multiply by an input, you add a bias term, you get an output, right? And then you apply nonlinearity, like a sigmoid function or a ReLU function. Now, matrix multiplication and addition is easy to represent as a system of constraints. It's just like you literally just write it down. But nonlinearities, you can describe a nonlinearity that doesn't even have a polynomial description, right? So what do? One strategy, which seems crazy but works, is there's a kind of argument called a lookup argument. A lookup argument, you create two giant columns, and you have the columns, the input, which represent the input and the output of a function. I take the input and the output that have happened in my circuit, like I mapped 1 to 1, and I mapped -3 to 0, and I mapped -2 to 0. I look those up in a giant table that lists -16,000 up to +16,000 and what they should go to, 0, 0, 0, 0, 0, up to, and then, right? And the argument that I make is that all of the values that I used in my proof, in my witness, appeared somewhere in that table, and therefore you can believe that I applied that function correctly. I'm showing membership in the function represented as a relation, as the graph of the function. So what we do is to represent all nonlinearities using lookup tables. Even something as simple as division, because division itself is not easy in a zero knowledge proof. Like I just want to prove I divided something by something and I got some answer. Like that's not even free. Because division in a finite field is not the same, produces the inverse in a finite field, which is not the same as the inverse in R. So it's the wrong answer for most use cases. So bits says, how big of a lookup table would you like me to use? This says, I'm going to write down, in order to implement the function, ReLU, I'm going to take 2 to the 16 possible values, plus and minus 2 to the 15. You know, from minus 2 to 15, I have to and write either 0 or the value for the case of ReLU, or if it's sigmoid, then I apply sigma. So
Okay.
that's the giant table, and that's also kind of why even seemingly small things take a little bit of time,
Wait,
but it's kind of a constant cost.
but also in the neural network, you are dealing with flows.
Right.
So how do you encode them for
That's
fine
an
tuning?
excellent question, and that's also one of the biggest difficulties in this. So the way that there are a couple of different choices you could make. The choice that we've made is to represent floats as fixed point numbers.
Mm.
We take, so suppose you take the input floats, like I showed in one of those input files, a bunch of floating point numbers. They're usually close to 1. Like often, we've normalized them so that there's like plus minus 1, right? We multiply it by a constant denominator, 2 to the 7, usually 2. So we multiply by 128, round them. That's our quantized fixed precision representation. So in other words, the number 7, the integer 7 means 7 over 128. Negative 5 means negative 5 over 128.
Okay.
Okay. And so that introduced a whole host of problems, which is why floating point arithmetic was invented. But okay, so you have this quantization. So one of the problems is, suppose I have a list of numbers represented this way, right? I'm tracking the denominator separately because they all have the same denominator. Okay, so I have a separate kind of denominator, which is like a type theoretic thing. Think about it like I have integers, 5, 10, negative 7, and somewhere else in the program I'm keeping track of what this denominator ought to be. And I take the dot product of 2 of those vectors. Now I've multiplied each of those, so now the denominator should be 2 to the 14. And then I have to, after that, figure out how to rescale it back down so that I can continue with the next layer. Or let it accumulate if I have enough space. So there's a whole host of problems that occur because of that. And the way they show up in a proof is something like overflow. So we have this 2 to the 16 bits. So if I take 2 things which are of scale 2 to the 7 and multiply them together, now it's sort of a scale 2 to the 14. That's okay. But now if I add a whole lot of them together, like 6 of them together, and they're not balanced, I can overflow this lookup table. And once I've overflowed the lookup table, now my proof will fail. Not because it was wrong, but it's a failure of completeness. It's not a failure of soundness. It's just I can't prove it because I got outside the lookup table. So what do you do? I'd say that's still currently an active area of research, but there's a couple of ways to mitigate that. One is, for example, in your training procedure, if you try to use balanced parameters, like you have a convolution, which is the dot product of something and the image, you could use all positive weights in your convolution, or you could use weights that sum to 0 in your convolution. If you use weights to sum to 0, it's less likely that you're going to overflow the next level up.
Will the CLI fail on that call, or will it?
It will tell you, you'll get an error that says something like, when it tries to verify the proof or run like a mock proof, there's a bunch of checks that happen along the way. One of those checks will fail, and it will tell you that a value was not found in a lookup table.
Okay, cool.
And we need to improve that to be smarter about saying, or you probably have an overflow, or here's what we should do.
Makes sense.
Yeah, that's
When
how
you
it
explain
will-
it.
That's how it will fail. Okay, so that's bits, a rabbit hole. We haven't got into how a lookup argument works. Probably won't, but the Halo 2 description is a really good one in the Halo 2 book. K equals 17 means that the number of rows that we've allocated in our table is 2 to the 17. Notice that 17 is bigger than 16 because one of the columns in the table is the lookup column. So if this K is smaller than bits, then it will give you an error that says not enough rows. And we're going to prove the input to the proof is the data. So the input.json, which is like one of those files that I showed you with some shape data, which is actually redundant, but some shape data, some input floats, some output floats that we're claiming. And then the model, which is given as an Onyx file. And then where to put the proof when it's done. Put it here. Where to put the verifying key. Again, this is because we use the same command for the setup phase and for the final phase. or for the proving phase, and where to load the parameters from. So let's try that. And I'm going to go back because it'll take a minute for it to load the KZG. We just changed our KZG parameters. We had it on the soft one, now we made it so that it can read real public things, but it's a little slower. Yeah.
Also, I'm curious on the data side of things. If you input, like, if you have more inputs and more outputs, would that change anything, or could you have one input, one output?
Yeah, you could have one input, one output. In fact, for lots of reasons, we want to try to minimize the number of things passed to the final bit. If we pass too much call data, all manner of things go wrong. And as this stuff evolves, that construction that you mentioned earlier, where you hash stuff, will probably get kind of built into the way things are deployed.
Yeah.
But that stuff's not automated yet. So that hopefully works. Still loading the parameters. Alright, so this command generates a proof that the model was correctly run on private inputs. So there's some flags that you can use to control whether the inputs are private or public, and outputs the resulting proof, and the verifier key. And the verifier key you'll need to verify it. If you were setting up and you're going to do native verification, like native binary verification, then you keep that key. If you're going to do EVM verification, we'll talk about how to do that. And we can also verify. This is still going. Okay. Here's the verify command. Oops, that's an EVM verify command. Is this Or we do a live demo. All right, we'll come back to that. The command generates proof, right? Okay, so we have a verify command. Verify command also has to know about the bits and the rows. It needs to know about the model. It needs to take the proof, and it needs a verifying key to check it against, and it needs parameters. And the parameters, if you change the parameters, you use a different ceremony, you won't verify, of course. Same with EK. There's also this table command. So the table command is fun because what it does is, oh, there we go. Okay, so this guy, well, that's the EVM verify. Okay, so this proof was generated. You'll see that the proof only took 2 seconds. Right now, it's just for some reason the key loading is, or the parameters loading is taking a long time. We'll figure out how to cache that or something so that doesn't happen. Let me do a verifier, which will also take a little while, mostly loading those parameters. So this is that verify for the same thing. And we'll go in a new window, and we can do some tabling when we do that. To display a table, do this. So this is the one change this. I only need EZKL because I've already compiled it. Okay, so this is the table command. So the table command is telling you what the strategy that the program has chosen to lay out the circuit. So this is a really simple circuit. It's a ReLU with just 3 inputs and 3 outputs. And you can see that it has 2 nodes. It has an input node and a ReLU node. It tries to take a guess at what the maximum of the output, so we can sort of try to help diagnose what's going on with overflow risk. It has a scale and in scale and out scale, and that's what I was talking about earlier. With that 7 means 2 to the 7. In this thing, the representation is that all the numbers are 2 to the 7 times the floating point number rounded. Sorry. And this has constant value. The constant value is like if in some cases there's a constant tensor and we want to keep track of what's going in there. And you see the ReLU has inputs. Its input comes from node 0. Its input dimensions are 3. Its output dimensions are 3. And there's some notion of index and bucket. And let's look at a more complex model. So if you ever want, you find a model in the wild that you want to try. Don't try to prove it first. Just try this table command, and the table command will tell you, do we know how to lay out the circuit? If we don't know how to lay out the circuit, send it to us or send us the error, and we'll try to figure out what needs to happen, be improved, or what new nodes need to be implemented. The fact that it knows how to lay it out is necessary but not sufficient to compute the proof. Well, mostly if it can lay it out, it will be able to do it as long as there's no overflow, but it might take some really long time. So like by accident, I had some error, and I set it a day and a half ago, I set it running on something in I64 max parameters. 9 billion parameters, and like I logged in today, and it was like, oh, it's still going, but it hasn't completed the proof. Well, I'm glad it's still going. But, you know, up to the heat death of the universe or something.
Yeah, question. Where in the repository do I find the list of all implemented ops?
That's a really good question. Is it written anywhere? I don't think so, but we should do it. Yeah.
Okay.
You can find it. It's not written like explicitly.
Yeah, it's
But we were just talking about what we're going to do is create a function, a Python function that says check graph, and we'll tell you if any of the ops are unimplemented. But we haven't made that yet. However, you can look at. Let me see, where is this stuff? I think it's here. This is the place where, yeah, okay, so this is the op kind code.
Okay.
Right, so this is telling you what we know how to do.
Yeah.
So we know how to do clip, prelude, leaky reloop, sigmoid, square root, divide, constant, source, add, sum, multiply, gem, which is matrix multiply, and add, more matrix multiply, dot, reduce, power, convolution, sum pool, average pool, reshape, flatten, batch norm, and pad. And that's all we know how to do right now.
It's enough for simple.
It's
simple-
enough for, yeah.
Yeah.
It's sort of enough for models that aren't super optimized. But,
Yeah.
Question. So,
Yeah.
what do you expect the, like, for example, size of network can support?
Yeah, it depends on how patient you are. We have, like, here, let me show you this model that, I'm going to show you this one. Okay, so this is a convolutional model that we just added this morning. Let's go to the Python for it. Okay, so this one is a nice little simple one. This is an MNIST model. So the input is 28 by 28, black and white. There's 2 convolutional layers. We know how to do ReLU, and there's 2 linear layers, very small, good enough to do digit classification. So conv, ReLU, flatten, matrix multiplication. If I table that one, it looks like this. Okay, let me look at this. So this is our layout strategy for this guy. It's a little small, but so you can see there's an input. You know, the way Onyx works, there's just a whole bunch of constant tensors that they just throw all at the beginning. And we have to figure out where they belong. So there's all these constant tensors. We have some guesses as to what their output max is at scale 7. Then there's the convolution, ReLU, flatten, affine, ReLU, affine. And so that's our strategy for dealing with that thing. That one takes about 1,000 seconds on my laptop to prove. Faster on a server.
1,000?
So about 1,000 seconds on laptop. Yeah. Which is a lot better than it was the first time we did it. So
Is there any like GPU optimization?
At the moment, there's 0 GPU optimization.
Just to-
I would say that okay. there's a lot of low-hanging fruit in terms of optimization right now in this package. And I would love anyone's help on thinking on GPU, on just rethinking, if you know Halo 2, rewriting the circuits to be more efficient, this kind of stuff. So I think in practice that should be at least an order of magnitude faster. Just have,
Have you compared the answers of this model to the original model? Because you are rescaling
Right.
things.
So there's some accuracy law. Okay, so that's another kind of worms, right? So when you quantize, of course, there's some accuracy loss. And right now, we're just quantizing in a cavalier way. We're not doing quantization aware training. If the loss is unacceptable, the paths are, increase the scale, right? You can decrease the scale to get some more performance gains. You can increase the scale to get closer to what you started with without overflowing. And then the other thing you can do is this quantization aware training idea. So all the different neural network vendors, NVIDIA and PyTorch and TensorFlow and everything have packages for quantization aware training where you say, okay, this is the quantization that's going to happen. We're dropping everything to I8s or I7s, whatever. And it will retrain and fine-tune the model to do better inference with those more approximate things, right? And people have gone crazy with this, and you can quantization aware training your model down to I4 or like I2, like 2-bit numbers, because that's really practical for inference in deployed devices, like get your car or whatever, right?
So I'm asking about like the practical. How much does this matter practically? Because I have no intuition how bad the model gets after this step.
It seems like so far not too bad, but yeah, I mean, for a big model, it might start to be more of an issue. But yeah, I'm not seeing a huge difference right now.
How are the output maxes estimated?
Oh, and by the way, this verification succeeded, verify click 0, loading the parameters took a little while. How are the output maxes estimated? It's not statistical, it's just you multiply the thing and you say what's the max value that it could be, and then you increase. So you keep, it's like a type theory thing almost. You keep a value along with everything that tracks the max, and then at each new op what can happen. So I have a value of max A and a value of max B, and I add it together, and now my max is A plus B. So I have a max A and max B, and I multiply them, now the max is A times B. And then when I divide by the constant, rescale down, then the max goes down. So basically every op has, as part of its logic, tracking that max value.
Okay.
It's like a... and hope to eventually use that max value, make it more statistical, as opposed to like an exact max, kind of like a guess system, given the distribution that we're seeing, how much room do we have? And these quantization aware training do a lot of that kind of statistical stuff to try to figure out how much reduction you can get away with.
Yeah, 'cause how come the 3 ReLUs with scale of 120 bits have different output maxes? The second from the bottom.
Yep, because another layer has hit it in between.
Oh,
And that increased the max of the alpha max, because the one of the dirty tricks we do is when we apply nonlinearity, we usually take that as an opportunity to reduce the scale. So you'll notice that convolution involves multiplication. So I've multiplied 2 things together, therefore if they came in at scale 7, they go out at scale 14. ReLU, or any nonlinearity, it goes in at scale 14, it comes out at scale 7, because we apply the ReLU, and then since we're creating a lookup table, I lied about what's in the lookup table, it actually combines the two things. It combines applying the ReLU and then dividing by two to the 7. So basically, anytime you hit nonlinearity, it's like a chance to bring things back down into a smaller range. And that can cause problems when, just because of the choice that we've made, when you have the rare circuit that, the rare model which doesn't have a lot of nonlinearities. Like if you just do a whole bunch of convolutions together or a bunch of affine transformations together without nonlinearity, then we never get a chance to do that. If that happens, you'll get overflow, and you can correct it by running one of these. I don't have the link right now, but there's a couple people who put out a graph simplifiers for Onyx, and they'll fuse. If you have two affine operations, you can fuse them. So it'll fuse that stuff, and that'll help with that problem.
Real quick, I'm sorry if you covered this earlier, but
No.
specifically what proof system are you guys using?
It's Halo 2.
Okay.
So it's
And
Plonkish with lookups.
have you considered looking at any of the more kind of wacky, modern, like lookup table stuff, like what's been coming out the last couple of years?
Yeah, so absolutely. And in fact, some of the design choices we've made are with that in mind. Although right now it's only Halo 2 on the background. But would very much like to include, for example, to replace the lookup argument we're currently using with CQ, to replace, to experiment with different commitment, the Fry commitments instead of KZG commitments, to try folding, all this stuff. So all this is kind of like on the roadmap, but we haven't built it yet. And it's an open source package. If anyone would like to, experiment with that with us, I would be delighted. I would be so happy to work with you. Right? I think those things are all possible. And when I say design choices, is because we built this as a stack, right? Where we treat Halo 2 as an API for creating constraints, and then on top of that, there's a representation of the tensors and the operations. And then on top of that is the client code, which is the Onyx file. So the Onyx file never has to change. We can change the way that the constraint systems are implemented by changing the proof system. So there's like a proof system as one of the arguments to this, and we hope that proof system right now, can do KZG and sort of IPA, but
It's definitely smart not to marry your stack to a particular proof system at this point in time.
yeah, it's going to be chaos for the next 3 to 5 years, and I think one of the biggest challenges in all of this is like, how do you navigate that chaos, right? And what kind of abstractions will work across proof system? Right now our research is coming out faster than we can keep up with. Anybody can keep up with the
It's
implementation.
like the record is being set, it's like you hold it for about 2 weeks for
Yeah.
for the proof efficiency time for lookup stuff, and then
Yeah.
someone else beats you.
Yeah.
It's funny.
And lookups in particular.
Mhm.
Although I think maybe, well, who knows? It seems like I actually think there'll be another jump in lookups. Like at least, you should ask yourself what's the theoretical?
Yeah, constant time proving that would be nice.
I've been thinking about like what is the measure of complexity for the nonlinearity specifically? What is the measure of complexity of the function that has to enter with lookup? Right? Like in this setup phase.
Well, the other thing is that from the little amount that I've looked into trying to do ZKML, it seems like you want to minimize the number of layers, right? Like that's what really blows your circuits up. So, from one side there's the proof system, but from the other side, what kind of neural net architectures work, more efficaciously with less layers, kind of thing is the other side of that.
Yeah. I mean, I don't know. The other thing is, once we get some kind of recursion, then the layers won't matter. We can do as many layers as you want.
Right.
Yeah. Or the layers will just require time. I hope that will be fixed soon, but. Right, okay, so. Where are we? That was the table, and then verifying with the app. Okay, so we're at Denver, and we're going to think about things that verify on chain. So let's dig into this question. So versus vanilla Halo 2, what do we need to change to get verification on the EVM? We need to change the equipment scheme. That's already, we've just made that the default for now. From the IPA equipment scheme to the D equipment scheme, we need to change the transcript the sponge, cryptographic sponge we're using for transcript creation. And we need to, instead of verifying natively, we want to verify in a smart contract. So we want to use either a bytecode or Solidity or Yule verifier. Okay, so we can generate a proof. We also need, we just need to remind it to use EVM transcript type, so that's controlling the cryptographic sponge. And just to say what this is, so every time you're constructing a zero-knowledge proof that it's non-interactive, you want to, you do a bunch of stuff as the prover, you commit to polynomials, commit to columns, make choices, and then you want to, in the interactive scheme that we're modeling, you want to ask the verifier, hey, send me a random coin flip, a random thing, random challenge, and I'm going to evaluate some stuff with that challenge. So every time I do something, I commit to something, I enter into a sponge, and the sponge is just, it's a stateful, it's like a hidden Markov model or something. It's a stateful machine. It has an input function where I can push stuff into it when I commit to it. It has a state, that causes a state transition. It has a squeeze function when I want to get randomness, I ask for randomness to come out, and that also causes a state transition. So different hash functions used to generate different cryptographic sponges, and that's how you perform the Fiat-Shinra transform in order to get to change an interactive protocol into a non-interactive one. So you produce a proof, you produce a verifier. So this is, again, we talked about K and bits, and we can ask Ezekiel to create an EVM verifier and tell it where to save. So it has the same inputs: what's the data, what's the network, what's the proof system, and then it will give you bytecode at deployment code path, which can be set directly to the chain, and it will give you to create a verifier, and it will give you Solidity code, which is more composable. Now, okay, the Solidity code is actually just a very little bit of Solidity code and a bunch of Yule, it's essentially assembly. Sorry.
No.
Someday maybe it'll be like
Works
more
the same.
legible Solidity. And then you can verify, and what verify EVM is doing here is just using Foundry, Anvil in the background to run that deployed code, bytecode, in order to get the verifier. And let's see if I one of these windows. Yeah, so this was the command prove with that. That was this command, and then I'll run the verifier creation. And while that's thinking about that, let's look at this document. Please read this document. Okay. So this was prepared by YG. And this is telling you a little bit about how to use the EVM part. So we are depending on the Snark verifier tool produced by the privacy scaling explorations team, and Han mostly team. And what they did was sort of a brilliant, crazy, what else could you do thing, which is they took the Halo 2 verifier, made it into generic operations. So you're calling a generic function at each step of the verifier, like each thing that you might want to do in the verifier. Computer pairing, check whatever, and then it has two implementations of those generic functions. One is just do it, native execution, and the other is append the appropriate command to the YUL code, right? And that's how we're generating the Solidity and YUL and EVM bytecode. So you generate the SRS, as we just said, or use the existing SRS, generate proof, and then run this create EVM verifier. That gives us the either the code both the code file, which is bytecode, and that when we want to actually call it using Foundry, we can, or a Solidity file that we can use that's composable. And that Solidity file has a verify function. So this is like the most important thing in a sense for when we're trying to build a demo or something, hackathon project, is you export this thing, and then your smart contract that's doing all the work will receive from the end user a claim. I ran this model, and this is the result that I got, and these are the public inputs for that, and it will send those public inputs and the proof to this verify function. This verify function will revert if the proof fails, and will otherwise just don't do anything. Okay? So it's a check. Yeah, I think we already integrated that.
So sorry, does it
Yeah.
revert or return false?
It reverts.
It reverts. Okay.
If that's not what you want, or you want to do something different,
Yeah.
let me know. We can probably make that. Would you prefer that it return false?
Yeah.
Yes. Okay.
It's just because of the interface. Why would you return a boolean if it's reverse, if it's false? Right?
Does it return something? Oh,
Yeah, it returns the
Returns a
boolean.
boolean.
Oh.
That's sometimes a practice too, it seems, but yeah.
I just want to make sure I'm not wrong here. Okay. Yeah, it still returns bool. Okay. So it's already what you asked for. I thought it reverted, but okay. We've gone through a couple different designs. And by the way, you probably want to. You can make a lot of predictions about whether a proof will succeed before you actually submit it, before you actually create it, right? So you can use a mock proof. You can look at what the result is. We also have a command to just called forward, which just lets you so these are all the commands. Table is the one that shows you the layout. Forward will just run the forward pass and tell you what the answer is, which is really handy because the answer you get will not be the same as the answer that the Python code would create because of quantization. So the forward will tell you what answer is the proof actually going to give you. What's the proof going to prove?
Okay,
Which you
that's
often
good.
need that exact answer.
Yeah.
And so, for example, if the forward pass you're trying to get to a particular value, that's the thing to check. You can tell immediately the client, your proof's not going to work, so I'm not going to bother finishing the proof for you.
Okay.
And mock proof is a little bit stronger way of checking that the proof. This one tries to decide from a Halo's perspective whether the proof will be able to be constructed, but it doesn't actually create the proof. So it's a bit faster, but it's not 100%. Sometimes the actual proof will fail even if mock wins or mock succeeds. Okay, sorry. So let me go back to this. Yeah, and you can also print out the public inputs and proofs in hexadecimal values, so it's pretty easy to pass it around. And the output looks like this. These are the public values, so this one is 0, and this is more than 0, and it's also more than 0, and here's the proof, which is just in hex. The public inputs are field elements, and this conversion. I mean, with everything, right? So like the hardest problem in cryptography is like serializing and deserializing stuff. Because all you know is like, this is a random looking string, but it's the wrong random looking string. Okay, so right now there's a limitation on the number of public inputs. which is pretty small, we're dealing with some problems with kind of contract size limit in EVM. So there's two types of verifiers available. One is the directly verify, and the second is the aggregation. So the aggregation, you can think there's a second step where we do a compression step on the first proof. It takes a fair amount of computation to do that. It's cheap, and it does a verification. The simple one, kind of how much work I have to do on the EVM side, increases as my proof gets more complex, right? So if I have a lot more columns, for example, in my proof, then every column is a commitment, and the commitments all have to be checked. And so my verifications work increases. In the aggregation, we kind of check all of that in another proof, and then the final proof is more constant size, essentially constant, I think. And so for when the model doesn't fit, you sort of have to go to, when the verifier doesn't quite fit in terms of gas or contract size, you have to start thinking about moving to aggregation, which is 2 steps instead of 1 step, so the development is more complex. Yeah, that's, yeah, okay, so then here's proof aggregation. This reduces the proof size, reduces the verifier time, and it requires a larger structured reference string, basically however many rows you need for the input, plus some more rows for additional bookkeeping and tracking and stuff. It requires between 3 and 6 additional rows, usually 6. I mean, sorry, not K has to go up by between 3 and 6. That's a lot more than 3 to 6 additional rows. And the way that works is a 3-step process. There's a single proof, which is essentially the same as the other kind of proof, except we've changed the transcript again. Okay, so now what's going on there? So we had talked about the transcript is a cryptographic sponge, right? I think a hash of an input I've added to this thing, it's stateful, and when I need to get a challenge from the as though it's from the verifier, I squeeze it, right? So native EL2 uses Blake. EVM, I think, is going to be Ketchak, and then Poseidon. With Poseidon, so Poseidon is a snark-friendly hash function, so it's algebraically implemented. So instead of being a complex permutation like Ketchak and SHA-256, it's basically a polynomial that you x cubed plus 1 or something that you apply over and over again, and you get some very high degree, very complex expression. What's nice about it is that it makes it because it's just a polynomial, it makes it easy to check inside of another snark. And that's why when we're producing the single proof, it's the same, except we have to switch to a transcript that we're going to be able to verify inside of the aggregate. We're using the Poseidon, which is a kind of hash function that is easy, snark friendly. There's still lots of research around these kinds of functions. We're reasonably comfortable using them for snarks, but not nearly as comfortable personally with them being cryptographic hash functions and collision resistant and everything else as we are ones that we've been using for a long time. Partly because things that are algebraic have a lot of structure, and I think we haven't necessarily tried every possible attack on that structure. So anyway, what does that say? It says, use that transcript. We're going to use a different strategy. Instead of single, we're going to use this accumulation strategy. Same other inputs. And we produce a proof. And then we generate an aggregate proof, which takes this proof as an input. In theory, it can do multiple proofs at the same time. So practically, because of the various limitations, you may only be able to fit like 3. But maybe eventually we'll be able to fit 10 or 100 or something. It's like a batch. And now we switch back to the EVM transcript, and then we input the proofs, the first generation proofs here, and we produce a new proof, an aggregate proof that we can then check. And then we can also create EVM verifier code for this aggregate proof. and we can verify ID. And you need solc to compile this stuff. I mentioned earlier that there's a way to pre-generate you can use a SRS that we generate for testing, or you can use one from this repo here, which is just a reformatting of this repo, basically. And that's secure to use for production stuff.
For the aggregation, what circuit are you using?
For the aggregation circuit, I don't remember the details, but it's the PSC one.
You must have some circuit to verify the proof. Right? That's how the aggregation works.
Yeah, sorry, I don't remember the details of how to answer that intelligently. What else? Let me talk about a couple of other parameters we have. Tolerance is kind of corrects for this numerical error problem. So like sometimes the result of running the Python, multiplying by 128 and rounding will only be off by like 1 or 2 from running the forward thing. Tolerance, if you make tolerance equal 2, that means each of those things are allowed to be plus or minus 1, 2 from at the very final output, which is just simple like x minus 1 times x minus 2. It's just a little polynomial constraint. And I talked about all of these other. Aggregate is the command that actually does the aggregation proof. Okay, I think maybe we'll stop and just chat and talk about examples and applications.
Yeah, applications. What kind of applications you imagine English for short term? Right now we can perceive imagine can address all long term maybe kind of ZKML, ChatGPT or some wild idea.
Yeah. Well, let me open the floor to anybody. I have, of course, ideas of what I think are cool applications. I mean, I'd say that my goal with this is not to build those applications, but to help support everybody else and help you all build those applications, right? Of course, we have ideas. So, anybody want to suggest any cool applications that is interesting?
I guess what we're doing for the hackathon would be like a kind of on-chain Kaggle thing. You can compete your models against each other without like showing what your model is, and you can verify that it was actually done off-chain.
What we're building is a scavenger hunt where you have an item and you can take a photo of it and verify on chain that it's the photo that is assigned by the people who made the scavenger hunt, and automatically get awarded Ether for finding it.
Ether? That's a lot.
It's still worth something.
But I have a question for your application of like comparing models without like showing the model. Is it like you are just hiding the parameters instead of like the network construction?
Yeah, so public input, public output, private params.
I see.
Yeah.
Well, actually, it's a good question. Is it like there's sometimes you want to hide the input but make the model evident, but there's also sometimes that like the input you want to be evident and the output, and maybe like the model can be opaque, and then you just want to prove the output has certain characteristics, but you're not wanting to prove the entire output. So I guess that's is there like flexibility for your thing in that regard, or is it just
so we were actually looking at a design like that for the scavenger hunt, which is that you could say, I have a target, a public target for my scavenger hunt, right? Like my image. Here's the public neural hash of the face. Find the face that matches this, right? Or you could have something else, like you just have a commitment to that thing, and then one of your private inputs is the thing you're trying to match. So you produce a proof that, you know, I know this target, I know this pre-image, and they match. You know?
When you say neural hash, is that like a property preserving hash function?
Yeah, I mean, for some things, like, so for identity, right? So suppose I want to do decentralized Face ID.
Yeah.
Right?
This is my face hash. How does that hash get generated?
Right, so for that kind of identity application, what you want is something that you know, produces, you know, take an image of a face, right, you know, lines things up and produces a vector that's characteristic of that face, and then next time I do it, I produce another vector, and then if they're close enough, then I consider it a match.
I see. So like the vector is the hash.
Yeah. So the output vector is the neural hash, which is it's a term people sort of use for that kind of thing. I think that's what Apple calls their thing.
I'm new to ZK stuff, but I mean, if you're, I mean, you're gonna hide the model, right? I mean, input as a face, you have a public output, and you'll try to hide the model between this input and output. But finally, if you have enough input output, and people will gonna guess, people are gonna kick it out all the parameters.
Well,
Yeah.
I think that the application for hiding the model would be if, let's say, some team comes up with a super cool system they want to keep proprietary, and you know there's some kind of reputation system associated with this model. It's like, you know, you can see, so the inputs and the outputs you can kind of see, like, okay, yeah, I want something that given this kind of input will produce that kind of output, but I don't know how the model works. I just know that this function is something I want.
There is something here because your model is, say, ChatGPT, it's very big, so it's difficult. But if it is small, then you can easily pick it out.
Right. So what you generally probably don't want to do is have a public model that protects all your money, right? Because someone can just reverse that model, or brute force it, or, you know, it's differentiable, right? So if the model's public, everybody knows it, they can figure out an input that will satisfy a particular output. So you have to think about it in terms of what is the overall crypto system? You know? Like, how do I control, is there another way to regulate whether I'm allowed to run this model or not allowed to query it? Or maybe I have to attach a signature to the image. Or maybe the output target passes through a hash function. Or maybe the output target is a private input and I've committed to it somewhere else. Or there's an MPC network that maintains an encrypted version of the model, and only if I meet certain on-chain conditions am I allowed to even run. You know? So I punt on that. It depends on it depends on the application, right? But it is important to remember that a neural network is not a hash function. If you give me the output and the network, I can figure out an input that will map to that eventually.
Yeah, along those lines, how do we prevent adversarial inputs? So, for example, people use the neural net on-chain enough to protect some value. It's possible for people to eventually find adversarial examples and abuse those.
Yeah.
So, is there like any prior research, maybe in the ZK space, that helps address like adversarial examples? Because right now, I think like the way is to just put the neural net in the gun and try to safeguard against those examples.
Acquiring transaction fees helps somewhat. It's not a perfect model, but yeah, you know what I mean? There's some cost associated with putting input in every time, then you can't just spam it forever.
Okay, so
Even if you have to produce the proof or something.
I'm not familiar with study on AI, but it's a similar thing. I'm familiar. There's some study with Bloom filters to do this kind of thing, where it's like preventing adversarial grinding attacks and trying to reverse engineer what goes into a Bloom filter. So if you were to Google like adversarial Bloom filter stuff, my guess is that you could kind of apply that to the neural net stuff. Although I think in practice, just requiring a transaction fee is the 80-20 rule for that.
Are you talking about a denial of service Bloom filter?
There's all kinds of reasons why you would want to prevent quote-unquote adversarial queries to a Bloom filter. I suppose that could be one of them.
about some more applications if you guys want to think about.
Yeah, what are your ideas?
Where are your ideas coming from?
Let me try one more time. View slideshow. Yeah, so one is the kind of KYC or document check thing that we were sort of talking about. You can say, all right, I'm going to take my phone and scan my passport, get the NFC data, proves that I have a selfie, maybe the phone, I use the phone enclave to sign the selfie so that I can control this problem of adversarial attacks, right? So my, Apple let me take a picture, or maybe it has LiDAR, so I had to have that. If I wanted to beat it, I would actually make a three-dimensional face that passes Apple's thing. And then it matches the ID, and the ID is not sanctioned. Then that produces a proof that that you can imagine of preventing something like what happened to Tornado Cash. Like, it doesn't have to be perfect, but if it reduces the unwanted activity on a network from 70% to 2%, might be enough to keep people at bay. And maybe we get a new regulatory standard. But let's hope that if that works well enough, at least someone will try to make it into law. Another thing is vaults. So a lot of people understand it as kind of a pure function, or you can think about the idea as being like you normally have a situation like a trustless vault, which has a predefined on-chain strategy. So vault meaning I deposit a bunch of money in a smart contract. Smart contract has some trading strategy or rebalancing strategy, like it uses different pools or it does something else. It rebalances like an ETF. I can either have a really simple on-chain strategy. It has to be simple enough to fit in a smart contract. Everybody can read it and trade against it. Or, but it's trustless and it's automatic. Or I can have a managed vault where there's a professional, and this is from someone else's this is the trade-off thing from Heroku. I can have a managed vault, which is someone is a professional analyst is running it, and trust that this person will download the data correctly, run it on their laptop, and upload it. And they won't decide that one day to create a new token and put all the money into that token, right? So it's sophisticated strategies. They can be secret, but they require trust of the manager. And if you do a ZKML strategy, then you sort of get the best of both worlds. The manager can commit to the strategy. You can imagine you post it, it runs for a month, and everyone can see how well it did. Then they decide to put money into it, and then it keeps going, and hopefully it does better, or continues to perform. And at least it's the strategy that it's always been run. And so there's different things like that. We're looking at people that want to build that. Prediction markets are kind of fun. So you can think about a small text story like who won an election, or a hurricane of a certain intensity hit Florida, or whatever, you want to pay out the insurance. In the beginning, you have to create a model that you believe will correctly decide who won the election from a snippet of text. Then to cause the payout to happen, anybody downloads from a trusted news source a signed article that says, Bloomberg says so-and-so won, or you can use a third-party notary to do that if you can't get the original provider of data to do it. And then, so anybody can download the model, run the model, submit the proof. Now everyone knows who won that. Now the chain knows what the outcome was, and it's a lot more efficient than something like a Gnosis protocol or something where you have many people vote on what happened, humans vote on what happened. There's a challenge period, other humans vote on those humans, there's staking, and there's token, just like one guy does it, uploads it, and we're done. So it's a much more scalable way to get information on chain. Prediction markets is probably not the best application, but you can sort of imagine Oracles is the more general thing. Thinking a little about fraud checks. So, most of the time when there's a hack in a smart contract, it's kind of, we all knew what the intent of the smart contract was, or all the depositors knew what the intent was, and in retrospect, the humans can be like, well, what that transaction was clearly not. It was, of course, in accordance with the code of the smart contract, but it was not in accordance with the intent of the smart contract. Someone able to exploit it to pull all the money out. So you can imagine if we can bake that human judgment of, yeah, that wasn't really the right thing, into the smart contract, or add a verifier, that reverts or returns false or kicks it up to a special committee or something, then when you submit your transaction, if it's over $10 million, you have to also submit a proof that reduces the chance that it's a fraudulent transaction. So that's something like that. That's
Could
a
be
pretty open design space, I think.
like kind of an alternative to Satora, like formal verification, but after the fact.
Yeah, it's like
Yeah.
an extra layer of defense that you
Yeah.
might be able to throw into a smart contract to kind of prevent bad stuff from happening. I like to say we're putting the smart back in smart contracts, and we're putting the A into DAO. So instead of humans making a judgment and then multi-sigs, you're running a multi-sig to implement that decision. We can just make it all on-chain with AI automation. So instead of working for people, we can all work for ChatGPT. Great. But no, it might make it possible to have DAOs that can decide on their own whether someone fulfilled the contract, that did the thing, that built fixed the issue that they promised they would fix on GitHub, or did the marketing campaign or whatever, right? As long as we can make a reasonable measurement and run a fuzzy check on whether or not the outcome is what we want it to be, we're good. These are the off-chain stuff, so something like AI bias. So I mentioned this in the beginning. Resume screening, for example, is now subject to a lot of regulation. A lot of places you have to have, the laws all say something like, if you use a AI model to decide who gets an interview, you have to have that model audited. What they mean exactly by audited, who knows? But this would make a way to kind of produce a proof that your screening algorithm was fair by running it against a test set and showing it has no, the bias is not too big in any direction. Training is interesting. Everyone always asks about, can we use this stuff for training? We don't want to do SGD in a snark because it's slow enough as it is. But what we can do is something like prove performance on a test set. So you can say, we're going to put this thing, like what you're doing, the cackle thing, right?
Yeah.
That is a way to do decentralized training with people. So, or you could maybe prove usurp some parameter space or something. Then there's other kind of things, like when we start combining it with other technologies like MPC or differential privacy, there's other cool stuff we could do, like I have a model and you have a genome, and we want to together prove that your likelihood of a certain disease is low, so that you can take that proof to your insurer and get the reduction. But if the answer is your likelihood of that disease is high, you don't really want anybody to know that it's you, because then your insurer will say, you've paid more.
Some kind of screen or scoring.
Yeah.
So it's also might be used for banking, like for your
Credit or something.
credit scores.
Yeah. So in that, maybe together we produce in MPC a proof. So you get a certification, but you don't learn my secret model, and I don't learn your secret genetic data. Then there's a complex construction. You can do differential privacy, where you say, I'm the data owner, and I would like to sell my data many times, or I would like to create marginal summaries of my data that have noise added to them, so that you can't tell whether any individual is in or out. This is what the census does, US Census, when it releases data. But data analysts prototype on the fuzzy, on the noise added, which are for differentially private result, and then when they want to know the real truth with a p-value, they send me a query, and I prove that the real data matched my previous commitment to what the database was. I use that data to create a noisy marginal, and when I ran the model in the real data, it produced the result that I gave. So you have a p-value, and you know that it's not fake data or synthetic data, it's real data, but you haven't learned, leaked any information that's against regulation. Provenance, so you can't really, it's possible to prove that a piece of generative content, image was produced by Midjourney or ChatGPT or something. Of course, that's sort of competing with the watermarking stuff. Watermarking is probably going to be better for this, but you could do it. It's probably also possible to prove that it wasn't generated by a particular model. Although I think that's significantly more difficult and requires further research to make that practical. But that's interesting. Another way to think about that is composable soft inference. So suppose I believe that LLMs will never be smart enough to understand science, but if I give them 10 facts, they can infer a fact, a little bit higher level of abstraction fact. As long as the context is small enough, and you could use the fact that I could prove that inference to generate kind of a tower of citations. And maybe you could use it to teach a model about physics or something, and have so instead of hallucinating, it kind of can prove all of its statements down to some. That's cool, but feels like
tree of knowledge.
Yeah. Wow. Yeah. Composable knowledge, something like that. Soft inference. So that would be pretty fun. More pedestrian thing is something like credit lead generation. I prove instead of submitting my data to a bunch of lenders they can bid on and steal my identity, I produce a proof of my characteristics, that I have enough money and my income is good and stuff, and then I only share them. So those are some more ideas. Tell me all your ideas. Tell me how I can help you make them.
Not necessarily an idea, but curious. Where would you recommend, like, for somebody new to kind of ZK, to look specifically to in the future collaborate on your repo? Like, look into Halo 2, or do you have any recommendations?
Yeah, reading the Halo 2 book is good. If you want to understand how Halo 2 works. We're trying to put up some more kind of good first issues.
Okay.
And you can just also let me know, and we'll try to
come to our house with help.
Yeah, pretty much all I've been doing the last 4 days is talking about this.
If anyone wants to build on this for the next few days, we're open until the 6th. And Jason's always going to be here helping you guys build. Just come over anytime.
Cool.
Yeah.
By the way, did you guys?
or whatever.
How are you guys gonna deploy the? This is more technical specific because you're also going to the challenges.
Yeah.
Like, how are you gonna build the server, or are you going to run the model on the front end?
Yeah, so we're gonna build just like a REST API that'll allow you to upload your Onyx file, and then it'll send you back the bytecode to deploy. So you can deploy your own verifier. First, you hit our API. We run the prove CLI command, and then just send back the bytecode to deploy.
Are you gonna use Axiom or?
Axiom would be cool, but like for the server, or like Axiom,
for the server.
Actix.
Actix. Okay. Yeah. Interesting, because I'm also doing the server part, and it's challenging.
Yeah. Got a little bit to figure out, but
is it only you two?
We're three.
And then four of us.
Okay, nice.
Yeah. What are you guys building?
I'm doing the scavenger.
Oh, okay, cool.
That's why I was surprised with one eat. I didn't know it was. I might try to hack it myself. Put a backdoor on the server.
Yeah. We were also like, or at the very beginning, I was like, I wonder if you could run this in WebAssembly, but there's no way.
Yeah,
you would have to port it probably if you.
No. So that would be a good, not first issue, second issue.
Yeah.
There's repos that show you how to make the Halo 2 prover run in WebAssembly.
Oh,
so that's done, and so like Nolin made this ZK Wordle thing.
Okay.
And that runs the proof and the verifier in WebAssembly.
That's pretty cool.
Other folks also have done that, so it's definitely possible.
Yeah.
You
can also transform like the whole ZKL crate into Wasmable, so that you can compile the whole crate into Wasm.
Yeah.
But that's a few days challenge, I guess.
Yeah, but it's probably not more. Like I think, 3 focus days can probably do it. Yeah.
So I'm still a little fuzzy also on the structured reference string. Do you want to keep that private if you're kind of the one like.
No, the structured reference string does not need to be kept private.
Okay.
Wait. In the usual use, the structured reference string does not need to be kept private. I think it leaks too.
Okay.
So I'm not sure that I'm just thinking there might be some cryptographic construction. There's some system you can construct in which you keep it private in order to restrict who can make proofs.
Okay.
You know?
Yeah.
That's sort of interesting. I don't know if that
No.
would
Okay.
But normally it's public, everybody knows it.
Okay.
It's interesting to ask what happens if you restrict access to it.
Okay.
Thinking about use cases in like small conflict resolution, maybe where you don't necessarily need to be anonymous, but the documentation you want to provide maybe has other information in it. Like you want to quickly get a response about a warranty, right? And the company isn't responding to you, or your tenant isn't paying rent, or these types of things. Have you guys thought about these? I think they're feasible.
I guess I don't understand the construction yet.
Yeah, so basically, like let's say that I bought an item from a company and it broke and it's under warranty. And they're not responding, and I want to be able to like think of it like kind of small claims, right? Like you're creating a judgment, right? Like the contract is making the judgment.
It's like smart contract as small claims judgment.
Right. Exactly. Yeah. So
cool.
I maybe send my bank statement, or I create a proof that has my bank statement that shows that I bought the item. I have a picture of the item, things like this. And I'm just like, I want to get a quick response, right? I don't want to have to sit on hold forever or whatever.
Yeah, that's a cool idea. Never thought of that. I think that's neat.
I think another interesting one would be like a virtual AI, like that dark forest, but instead of using just math, having AI algorithm. I think there could be very simple ones that would make that, for example, dark forest even more appealing.
Or you can add players.
Yeah, and like I don't know, like you're playing the game, then the AI generates a little monster, and then once you kill it, you can prove it and then claim some things on chain, or ownership of some area on chain.
It was not about like using it as the monster AI, which is nice because that the game setting is nice because then like even if the monster's not that smart, the game is that you figured out how to make the AI. It's okay. It's not that smart.
It's a bit fun.
I was just thinking about variable rate gradual Dutch auctions and how they're basically NFT auctions that have a schedule based on after how many days how many NFTs should be sold, and it adjusts the price of the NFT over time based on if the schedule is ahead of time or behind time. And if you could use AI to add in some more metrics to that, so maybe the activity of the website, the market itself, and see if any extra data can make more accurate price adjustments for auctions. I think that would be cool.
Or like anti-market manipulation.
Yeah.
So like you can't spike. It's harder to spike a price or something.
Exactly.
Yeah.
Exactly.
It'd be funny to have like joke AIs that you can like wager on like who's the most rad, and it's just a model that is trained on rad things. And so it's like, I bet I'm more rad than you.
Things are good. Like simple.
Yeah, I think the simplest ones are the kind of the most fun as well. Play around with for now.
I previously actually built some modular for a project. It's actually I think the situation is similar, but I don't know. But I have no knowledge of ZK, but the situation is quite similar. Actually, for airdrop, you're gonna send say a lot of token to 10K people, right? The transaction fee is going to be very high if you send one by one. So what we do is like we have a verification function, and it's like model, right? We put it onto the Ethereum contract, and we put a result there. It's like a multi-proof root result there. And people, rather than send one by one, we let people to go there and say input their address and amount, and then do the verification, and they get it. And the transaction is actually gonna be paid by every user rather than us. Yeah.
Yeah, that's cool. Yeah, it'd be awesome for airdrops because it's work to produce. If it takes you 5 minutes and you have to have a decent laptop to produce the proof, it helps rate limit it. And you're producing a proof that you have the right characteristics, and
Yeah, I think that would be amazing.
Getting your deposit back when you rent somewhere. Right? That's locked up in a smart contract.
Yeah.
Leave your Airbnb and take a picture that I haven't trashed the place.
And Jason, have you heard of altered state machine? They create NFTs with AI models in the smart contract, and I feel like that would be extremely relevant if you didn't want the NFT to, or you wanted the model of the NFT to be private. They use it for gaming, so I think they have like a racing game where the players are NFTs, and you can own a player. I know they have a boxing game where you have an NFT that is a boxer, and it's an AI. I think it would be really relevant in gaming, like the Neil said.
Well, it seems like we have them all also. Thank you everyone. And like, if you're interested in contributing, let us know. We're trying to figure out issues. If you have problems using it, let us know. We'll fix those as fast as we can.
So if someone wants to contribute, how can they find you?
You can find me on email or on Telegram. That's a question. On Telegram, I'm awesome.
I mean, we're open till 6, so like,
yeah.
just go.
I can show you my code. It's also on this. Also, Jason on Telegram, or Jason Morton on Twitter, or on the repo. Or you can open an issue and repo.
Yeah, thank you.
Thank you for coming.
Thank you.